Okay, 6.1 is titled Factoring a Monomial from a Polynomial. So what we're really going to concentrate on today is pulling out common factors, or finding the greatest common factor between two different terms. And that's what all of your homework on Pearson is. I went through and checked through all of it. And so before we can pull out the common factors, or the common monomial, what we have to do is understand what a factor is. So if you have A times B, then the A and B part of that equation are the factors of C. It's what we can break C into that equals the factors. And so sometimes you're going to be asked to find all of the factors of a given term. And when we think about numbers, a lot of times we can think of what times what will give me a specific number. But when we start adding variables into it, there's a lot more that actually that combines with our factors that we have to take into consideration. It's not just 2 times 3 will give me 6, or 1 times 3 will give me 6. We also have this x to the third term that we have to consider when we're kind of trying to find all of the different factors. And so if you have to approach a problem like this very first one, find a system that's going to work for you. Find a way that you're not going to forget to look at a certain type of factor. And here's what I mean. My whole first column that I'm going to focus on, I'm only going to think about factors of 6. What times what will give me 6? I'm not going to be concerned about the x to the third power right now. I'm just going to concentrate on how do I break down 6, because that's going to help me to stay organized and not forget any of the factors. So the easiest factor to start with is 1. 1 times 6x to the third will give me 6x to the third. That seems like a duh, but it is a factor. 1 is a factor of everything. So then I go again and I say, okay, well I know 2 is a factor of 6. So if I take a 2 out, what will I have to have left? 2 times what will give me 6x to the third? 3x to the third, exactly right. Okay, then I do it again. Well, I just said that 3 is also a factor, but that'll make this 2x to the third. And our last one will be 6 times just x to the third. Or if you want, you can put 1x to the third. Either way is correct. Just traditionally, we don't usually include the 1 in front of a variable. It seems a little bit redundant. But here I have split apart my 6 into all of the different versions and factors that I can. I left my x to the third alone for right now. But each one of these pairings, this is a factor, this is a factor, this is a factor, this is a factor. So all of these are factors of the 6x to the third. Now I'm going to move over to the other side, and I'm going to start pulling out my x's and playing with them. So the first thing I'm going to do is I'm just going to pull out 1x. If I pull out an x, then over here I have 6x squared. Now what if, because I'm kind of going to try and go in the same pattern that I went here, just to try and keep it simple. If I pull out a 2x, 2x times what will give me 6x to the third? 3x squared, yeah. 6x to the third. Again, I'm going to kind of keep going in the same pattern. If I take a 3x out, that'll leave me with a 2x squared. And then if I pull a 6x out, that'll just leave me with an x squared. So theoretically, if I went and tried to do this again by pulling out x squareds, look what would happen. If I pulled out an x squared, it'd be times the 6x. If I pulled out a 2x squared, it'd be times the 3x. It's just the opposite of what I've already listed. So I've actually already listed all of the x squareds as well. And over here, I have my x to the third. So just in these two columns, I have actually listed out all of the possible factors for 6x to the third. There's 1, 2, 3, 6, 6x to the third, 3x to the third, 2x to the third, x to the third, x, 2x, 3x, 6x, 6x squared, 3x squared, 2x squared, and x squared. All of these are factors to 6x to the third. And they're all from just our columns. So that's why I like to go systematic, because if not, I'm very likely to leave something off. And so I pulled out the 1, 2, 3, 6 in my first column, so I pull out the 1x, the 2x, the 3x, and the 6x in my second column. And the reason why we need to be able to break down our numbers or our terms is because we're going to be looking for what's known as the greatest common factor as we progress. And if we don't know how these things break apart, then we're not going to be able to find that. Because when you're finding the greatest common factor, as we will see in a few minutes, we're not just looking at one term, like a 6x to the third. We're looking at a 6x to the third compared to a 36x squared and trying to figure out what these two things have in common. And so being able to list their factors or come up with the greatest factor is going to help us. Are there any questions on this? Okay. So when we start factoring, a lot of times what we're looking for is we're going to be looking for prime numbers. We're going to keep factoring things until we get to prime numbers a lot of times. And so we need to understand what's the difference between a prime number and also a composite number. Those are the two main distinctions of our numbers. A prime number is an integer greater than 1. That's a special rule. That has exactly two factors, itself and 1. So 1 is not considered prime because you have to be greater than 1 to be a prime number. But 2 is prime. The only factors for 2 are 2 and 1. That's it. If you can come up with a different factor for that, then it's not considered a prime number. And so I just listed out the first handful of prime numbers, 2, 3, 5, 7, 11. You can see as they keep going. And you'll notice, or maybe you will notice, 2 is actually the only even prime number. Every other prime number has to be odd, because if you're not odd and you're an even number, then 2 is going to be a factor. So 2 is the only even one. So if you end up with an even number somewhere, you know at least that you have a factor of 2 that can be pulled out of it. You don't have to memorize a big list of prime numbers, but if you can identify some of the main ones, mostly the ones like under 20, if you recognize those, then when you hit those later on, when you're taking the factors of things, you'll know, okay, I'm done at this point. I hit my my prime number, I'm good to go. Composite numbers are like the opposite. They're all the other numbers. It's an integer greater than 1 that's not prime. So it has other factors. 6 was not a prime number. 6 had 1 and 6, yes, but it also had 2 and 3. So it was not a prime number. And just as a random factoid, 1 is considered neither prime nor composite. Notice both of our rules for prime and composite said that you had to be an integer number greater than 1. So 1 is just kind of there. It's not considered prime or a composite. It's just special. Now, as we progress and we start looking for the greatest common factor between two terms, one of the easiest way to do that, I think, visually, is to do a factor tree. Has anybody done a factor tree? Yes, no, maybe. You are not required to do a factor tree to find these prime factorizations. I will use a prime factor tree just to show you how to do it, and if you have another method that you prefer in breaking these down, that is totally fine. I like factor trees because they are very visual, I think they're pretty simple to utilize. So we are going to find the prime factorization of 48. Or another way of stating that is write 48 as a product of prime factors. Both of those are asking for the same thing. It wants us to break down the number 48 into just a whole bunch of prime numbers. Because 48 right now is not prime. We know that even if we don't know all of our prime numbers because it's even. And if it's even and it's not the number 2, then it's not prime. So here's how a prime tree works. You put the number, or a factor tree works. You put the number you're trying to split up at the top of your tree. And then you think, what times what will give me that number? And maybe you don't know straight off the top of the bat anything that gives you 48. And that's okay. If it's even, I know a 2 will come out. So I can take out a 2. 2 times what will give me 48? 24. Now 2 is prime. So as soon as you hit a prime number, your branch is done. Like it stops moving. Now what times what will give me 24? 2 times 12, okay? 2 is prime. What times what gives me 12? Okay, we're going to keep going with the 2s, I see. And then 6 is 2 times 3. So our branches stopped at 2, 2, 2, 2, and 3. So the prime factorization of 48 is 2 times 2 times 2 times 2 times 3. Or if we wanted to shorten that, it would be 2 to the 4th power times 3. And here's something that's nice about the factor tree. Who can tell me something else? What times what will give me 48? Maybe a number bigger than 2. 12 times what? Awesome. 12 times 4 will give me 48. Now, neither of these are prime, so I can split both of these. 4 is 2 times 2. 12 is what? 3 times 4. I'm going to write the 4 over here just so it doesn't get cluttered. 3 is prime. 4 is not. We already said it's 2 times 2. So this tree looks very different than this tree. But the prime factorization still works out the same way. We have 1, 2, 3, 4 2s and 1 3. So no matter what your tree looks like, as long as you've done your factoring correct, you're going to end up with the same prime factorization. That's not the only 2 options for 48. You could have done 6 times 8. You could have done 2 times 24 and then split differently down there. So there's many, many different ways that your tree can actually look. But regardless, you're going to get down to 4 2s and 1 3. And so that's kind of neat. I like factor trees. I think they're a great organizational tool, and they're very visual if you are a visual learner. And we will see they're very helpful when we try to come up with the greatest common factor, which is the next thing we're going to do. Are there any questions for how I utilized the factor trees or came up with a prime factorization for these numbers? All right, let me flip my notes over so you can see why we're doing it. The why for the factor trees is so we can find the greatest common factor between 2 or more numbers or expressions. If you like steps, these are the steps that you will go through. The first step is find all the prime factors of the given numbers or the given expressions, aka do a factor tree. Break it all apart. Let's find it all. Then, after you've done that for both of your numbers or your terms or all of your numbers and terms, because it says 2 plus, so you could have 3 or 4 or 5 different terms that you're looking at. Once you've factored them all down into prime numbers, what you're going to do is you're going to determine which of these prime factors that they all have in common. Which ones are shared? Because that's where the common comes in. They have to be in common with all of the terms. So you factor it, you find what's common, and then in order to find the greatest part of the greatest common factor, you have to multiply all those common factors together. So the name greatest common factor is literally the steps that you're doing, just kind of in reverse. You have to factor it, then you find what it has in common, you multiply all those common things together to figure out the greatest. looking through the Pearson homework, I am 99% sure that's all of the problems are finding the greatest common factors. This is a very important tool to be able to really hone right now before things get more complicated. So we're going to do a handful of problems like this. We're going to find the greatest common factor, and the first one's for 90 and 126. That funky little symbol in there, that's my weird ampersand or and symbol. That's not some weird math thing. It's just how I write and. So in order to find the greatest common factor for 90 and 126, I'm going to do a factor tree. What times what will give me 90? 2 and 45. That works. That's the one I did in my notes, my handwritten notes. Maybe that's not what stands out. If it ends in a 0, 10 is always a factor. It would be 9 times 10. That would give you a factor as well. Either of those work. I'm going to do one that's not like the one in my notes, just so you have two different references. If you go back and look at the paper notes, you'll have 2 times 45. If you watch the lecture video, you'll have 9 times 10. And you'll see that it still works. 9 is not prime, because that's 3 times 3. 10 is an even number, so it's not prime. That's 2 times 5. But 3, 3, 2, and 5, those are all prime. So my tree would be done at this point. So I have factored 90. Now I need to go factor 126. And off the top of my head, the only factor I would know to pull out would be the number 2, again, because it's an even number. And then I'd say, okay, 2 times what would give me 126? Well, 2 times 63 would give me 126. 2 is prime, so it's done. Now here, I would have to determine if 63 is prime or not. And it is not. You are correct. 6 plus 3 is 9. 9 is divisible by 3, so 63 is divisible by 3. 3 times 21 would give me 63. And then 21 is still not prime. That's 3 times 7. So these trees are obviously very different. 90 is different than 126. But if we look at their end branches, we look at the ends, the 3, 3, 2, 5, and the 2, 3, 3, 7, they do have some stuff that's in common. And that's what we're looking for in our second step. What terms do they have in common? Well, this one has a 3. This one has a 3. This one also has another 3. And this one has another 3. This one has a 2. This one has a 2. But the only number remaining at the bottom of my tree for 90 is 5, whereas the last remaining number over here is 7. Those are not the same. So I'm not going to circle those. Those are not in common. So the last step is the multiplication step, where we take 3 times 3 times 2 to determine what the greatest common factor is between 90 and 126. 3 times 3 is 9, times 2 is 18. 18 is our GCF for 90 and 126. Are there questions on how I did that? Before I start throwing letters in with it. Do the factor tree. Yes?
I just wondered, where did you get the 9 and the 10?
So I was asking what times what will give me 90.
Okay.
9 times 10 gives me 90. And so then I keep breaking these down until I hit prime numbers.
Okay.
Does that help?
Yes.
Cool. Other questions or clarifications? Okay. This is intermediate algebra. So algebra is in the title, so let's throw some letters with this. Let's make it algebra. and we're going to add a third term. So now we're not just concerned with the greatest common factor between these first two, we're concerned about the greatest common factor between all three of these terms. And yes, there are variables at play. Most of the time, the way that I approach these problems is I deal with the numbers first, and then I deal with the variables second. Because yes, you can do a factor tree with the variables. In my handwritten notes, I do split the variables as well. But I'm also going to talk to you a different way about doing it, where you don't necessarily have to do a factor tree for the variables, and you can just consider the factor tree for the number. So let's do our factor trees. I'm just going to do them for the numbers, and we will talk about the variables in a minute. So what times what will give me 18? 3 times 6. 3 is prime, 6 is not, 6 is 2 times 3. In my handwritten notes, I said 18 was 2 times 9, and then I split my 9 up into 3 times 3. Again, you're going to get the same prime factorization. 15 makes for a really short tree, because the only factors of 15 are 3 and 5. 27 is 3 times 9, and 9 is 3 times 3. So now I have my 3 numerical factor trees. Numerical means number, so I only factored the numbers. So I'm going to look for what do each of my trees have in common with each other. Do you see anything that they all share? A number 3. This one has a 3, this one has a 3, this one has a 3. Notice on these two, there's more than one 3. But because the 15 only has one 3, I'm only having one circled, because that's the only thing they all have in common. They share one 3. They don't share 2 3s or 3 3s, they just share one. So my greatest common factor so far is 3, but now I need to consider my variables. I have a y squared, a y to the third, and a y to the fifth. So you can do factor trees with these as well, or you can say, okay, I know they all have y's, and they have second to the second power, the third power, and the fifth power. So what do they all have in common? Y squared. Because y to the third is the same thing as y squared times y. Y to the fifth is the same thing as y squared times y to the third. So they would all share a y squared. So you can still do a factor tree of sorts if you want to, but a lot of times what I do is I ask myself 2 questions. Do they have the same variable? And in this case, the answer is yes, because they're all y's. And then I look and say, okay, what is the biggest amount of y's, or the biggest amount of that variable that I can pull out that they all have in common? And these splittings that we're doing here, kind of this mock tree of sorts, this is from our product rule from 5.1. So all that stuff still is active and in play. We're not just learning stuff to forget it. So they all have a y squared, so my GCF is 3 y squared. I said 3 as I was writing the 2. The question you want to keep asking yourself over and over and over again is, what do they have in common? That's the question you ask yourself when you're doing these GCF problems. That's the question you're asking whenever you have a fraction and you're trying to figure out if it's actually simplified or not. What does the top have in common with the bottom? Because this is what we're doing. We're factoring out what they have in common and canceling those things when it comes to fractions. Let's do another one with variables. Because with adding the variables, I know is different. So again, though, I'm going to focus on the number first. I'm going to find the GCF of the number, and then I'm going to look and examine my variables. And luckily, we've already done a factor tree for 48. We did it 2 different ways just a little while ago, right here. So I'm going to do it a 3rd way, just so you see that there's all kinds of ways to factor 48. I'm going to say 48 is 6 times 8. 6 is 2 times 3. 8 is 2 times 4. 4 is 2 times 2. Again, completely different factor tree, but notice we get 1, 2, 3, 4 2s and 1, 3. Same thing we got earlier. Then I'm going to move over to 60. Again, 60 is a number that ends in 0. So right off the bat, I can think, okay, I know 10 is going to be a factor. 10 times what? Well, 10 times 6. 10 is 2 and 5. 6 is 2 and 3. So if I'm looking for common things, what am I going to circle? What do these two trees have in common? I heard the 6, yes. Since this one we did factor with 6s, you can actually see that they have 6s in common. In my handwritten notes, I didn't factor 60 as 6 and 10. I factored it as 2 and 30, and then 2 and 15, and 3, which is 3 and 5. So you wouldn't actually see the 6 initially. But yes, I usually go all the way down to my terminal ends of my trees, just so that I don't get confused and accidentally circle things more than once. So they have the 2, they have the 3, and they have another 2. Now at this point, the only thing left in this tree is a 5. There are no 5s in this tree, so that's it. So my GCF will be 2 times 2 times 3 for the numbers. And then I have to look at my variables. I have an x squared, a y, and a z. I have an x to the third and a y to the third. So this one, my 60, doesn't have a z at all. So I know z is not going to be a common factor, plain and simple. But both of these do have x's. I have an x squared and an x to the third. So I can write x to the third as x squared times x, which means they share an x squared. Then I look at my y and I say, okay, I only have one y on the left side. I have 3 on the right. I can write y to the third as y times y squared, and they have the y's in common. So my GCF, 2 times 2 is 4, times 3 is 12, x squared, y. That is the biggest thing I can pull out of 48x squared y z and 60x to the third y to the third. And actually, we could write 48, as you showed me earlier, as 12 times 4. We can also write 60 as 12 times 5. And so if you see that early on, and you notice, okay, wait, it's just 12 times 4 and 12 times 5, they're going to have 12 in common, then you don't necessarily have to take your tree all the way to the bottom if you don't want to. It just depends on how you're factoring in the beginning. And if you're not great with your multiplication and your division tables, this is a good time to get sharpened up on that. Use the Khan Academy links that are on the Blackboard site. Get flashcards, do those stressful 1 to 2 minute tests where you try and cram all those out really fast. They really do help. Are there any questions on how we did any of these factor trees? Or how we found the GCFs? Okay, so 6.1 was titled Factoring a Monomial from a Polynomial, and we haven't actually done that yet. We've done a lot of factoring, but not of polynomials. So let's do that, since that's what this chapter, or this section, is all about. There's not a lot of notes for it. We're going to do some examples. When you are factoring a monomial from a polynomial, what you're really doing is the reverse of the distributive property. Now, if you don't remember what the distributive property is, I can give you a little quick refresher. Distributive property is where you have a number or a term out front of a set of parentheses. And what we end up doing is we distribute that or multiply it inside to each of the terms so that we have AB plus AC. What we will be doing when we factor a monomial from a polynomial is we start with this right-hand side and we say, okay, we have AB plus AC. What do both of these terms have in common? They both have the A, so I can pull the A out, and that leaves me with the B plus C. So we are going backwards. We're still using the distributive property and concept, but we're going to be going the opposite direction. And regardless of if you are trying to find the greatest common factor, or if you are trying to factor out a monomial, factor out something that they have in common, what you're doing is you're asking over and over and over again, what do they have in common? If you have 2 terms, what do they have in common? If you have 12 terms, what do they have in common? What can I pull out? And you don't necessarily have to use factor trees in these instances. Most of the time, you probably won't need them because the numbers are going to stay relatively small and friendly. So for the first example, I have a 7x plus 28. So this is a binomial. I have 2 terms. And what I'm asking is, what does 7x have in common with 28? Does it have anything? It has a 7 because 28 is 7 times 4. So if I pull out that 7 to the front, thinking about this is the reverse of distribution, if I take the 7 away, 7 times what will give me 7x? Well, x. Then I go to my next term and I say, okay, 7 times what will give me 28? It's 4. And these are really nice in terms of maybe it's going to take a minute for it to click on how exactly I'm finding these other numbers, but I can always check. Can always check my answer by redistributing it. If I take 7 times x, I get 7x. If I take 7 times 4, I get 28. So it checks. You can automatically do a self-check on it. And that's it. You might be tempted to say, okay, now I got to set this equal to 0 and I got to find what x is. You're not solving anything. We are simplifying. We are factoring. We're not solving. So don't set anything equal to 0. Don't do magic math. Questions on that first one? All right, let's look at B. B, we have 8q to the third minus 20q squared minus 12q. So each of these terms has a numerical part and a variable part. So look at it just like we were factoring and finding the greatest common factor a minute ago. Do the number part first, then do the variable. So if I look at the numbers 8 and 20 and 12, what do those all have in common? 4. They do all have a 4. So that will be the number that I pull out front. Now, before I put my parentheses and do the rest of it, now I'm going to consider my variables. I have a q to the third, a q squared, and a q. So they do all have the same variable. They all have a q. So what is the biggest amount of q I can pull out? Just the 1. Because that's the only thing they will all share. Now I can do my parentheses and I say, okay, 4q times what will give me 8q to the third? 2q to the second. 4 times 2 will give me my 8. And then if I take a q out, I have to have q to the second left in. That's the first term. Then I shift over and I do the exact same process for this minus 20q squared. Minus 20 means it'll be minus in here because we pulled out a positive. 4 times what gives me 20? 5. And then q times what would give me q squared? Q. Then I shift over again, and it's a minus 12, so I'm going to put minus. 4 times what gives me 12? 3. And then I don't need to have a q in here because there's only one q with my 12, and that q is already out here. So when I distribute, that q would get brought in, so it's just a minus 3. I pulled out absolutely every single thing that it had in common. Now, let's say you're in a rush, or you notice first that 8, 20, and 12 are all even. And so you don't pull out a 4, you just pull out a 2. That's okay. If you would have not seen the 4 and you would have just pulled out a 2q, that would have left you with 4q squared minus 10q minus 6. This is where you would pause and say, wait a second. All of the numbers inside my parentheses are still even. That means I can pull out another 2. And when you pull out another 2, it takes you up to the final solution. So even if you're not sure what the biggest thing is that you have in common between all of these terms, and you don't necessarily want to do a factor tree for everything, pull out what you do know and then look inside and say, is there anything else they have in common? Even when I get to this stage, I would look and say, does 2, 5, and 3 have anything in common? And the answer is no. Those are all prime. So I would stop at this point. But if you don't notice the 2 or the 4 at first, pull out what you do know. And then look and say, is there anything else I can pull out? And then keep pulling out until you're done with that problem. Questions? All right, we got 2 more. This next one is super important because what we're really doing is factor by grouping. Chapter 6 is going to be the factor chapter. We're going to learn lots of different ways to factor, but this one's still grouped in because we're really looking at 2 terms, and we're asking what do these 2 terms have in common? And you may be tempted to try and distribute each of these first, and I don't recommend doing that. We have 2 terms at play. We have this first term, which is the x times the 5x minus 2, and we have the second term at play, which is 7 times the 5x minus 2. So looking at those 2 terms, what do they have in common? The 5x minus 2. That whole set of parentheses is the same thing in the green section versus the purple section, or in the first term versus the second term. So I'm going to pull out that entire set of parentheses, the 5x minus 2, because it has the same thing here as in here. And then here's the nice thing. Whatever was out front is what's going to go in our next set of parentheses. We had an x, and we had a plus 7. It's factored. It's done. We looked and said, what do these have in common? We pulled it out to the front. Just like we did on these other examples, we pulled it out to the front, and we put whatever was remaining inside of a set of parentheses. What was remaining was the x plus 7, and that went inside the parentheses. You do not have to factor this and FOIL this or do anything else. You have done what it asked you to do. You pulled out what it had in common, and you've written it appropriately. But seeing that this 5x minus 2 here and here pulls out, and then we have this x plus 7, that's big because when we factor later on, especially our quadratics, this is one of the methods that we will utilize. And like most things in math, if it doesn't click the first time, repetition is the way to do it. Keep practicing. It gets easier. Use that similar question button in the homework. Give yourself more examples to try and work through. The more you see, the easier it becomes to actually see the patterns and the way that these work. Okay, so I have 8x squared y, 12x y squared, and a 5xy. So the first thing I'm going to look at is the numbers. 8, 12, and 5. What do these have in common? Huh? Nothing. 5's prime. 5 doesn't go into 12 or 8. So nothing goes into all 3 of these. Yes, 4 would go into 8 and 12, but that doesn't go into 5. And so when we're looking for common factors, it has to work for everything or it doesn't work for any of them. So there actually is no numerical common factor. So then I look and I say, okay, I have an x squared, an x, and an x. Do they have anything in common with those? Yeah, they have an x. This one has 2, but these other ones only have 1, so I can only pull out one x. And then I do the same thing for y's. I have a y squared, and a y, so I can pull out one y, which would leave me inside my parentheses with an 8x, because my y would come out front, plus a 12, the x would move out front, one of the y's, so just 12y, plus, and then at the end I just have a 5. If I redistributed my x, y's inside, I would get back up to our starting point, which is always what you want to do when you're doing these factors. If you redistribute, do you go back up? Because if the answer is no, then you've done something wrong. You can always check these with your distributive property. Are there questions on these?